Hello, this video will cover section 3.4, exponential and logarithmic equations. We will be solving simple exponential and logarithmic equations. We will solve a little more complicated exponential equations after that, and then, of course, more complicated logarithmic equations. And we will be using exponential and logarithmic equations to model and solve real-life problems. So we will cover some applications there. So we have, there are two basic strategies for solving exponential or logarithmic equations. The first one is going to be based on the one-to-one properties that we discussed in the previous sections. So, and that was also, we could use that with exponential and we could use it with logarithmic equations. So with exponential, we used to have something like, I don't know, 3 to the power x, and then here we had something like perhaps 27. And the key here is to rewrite the 27 so that it has the same base as the left side, so it will be 3 to the power 3. And then from here we could say that if the bases are equal, then the exponents must be equal. With logarithms, we had something similar. I'm just writing a very simple one to refresh your mind. So if you have natural log on both sides and just one on each side, then you can cancel that out and you will get x equals 2. The two arguments are equal. And so the second strategy is based on inverse properties. So we've been discussing since 3.2 how an exponential and a logarithmic functions are inverses of each other, and so one will undo the other, and so that's why it's important to learn both, and that's why they're both in the same chapter. So we are gonna work some of those both ways, one-to-one properties and inverse properties. And so right here is an example again. So one-to-one properties, you have the base is the same. And so because of that, the exponents must be equal, if you are saying that this statement is true. So, and we have the if and only if. It's a double arrow. And it implies that if the left side is true, the right side must be true. If the right side is true, the left side must be true. So you could use this property in both directions, because it is, I can't think of the word of the statement. It will probably come back later. Okay. So for logarithms, same thing that I was showing with natural log, but here this log base a on both sides. And we have the arguments x and y, so then x equals y. And again, it's a if and only if. The abbreviation for that is an I with a double F, and it is, we have this double arrow. I can't think of the name. Okay, so I remember, in fact, I had to look it up, but they are conditional statements. Yes, that's what I wanted to say. So like a if, then, that is a conditional statement. So then this one works in both directions. So it's a double conditional statement, and that is true for both of them. Okay, so the inverse properties, we have this one that if you have a number, or a number, that's the base, being raised to an exponent that happens to be a log of the same base, then that will undo each other, and then the answer will just happen to be whatever the argument was for that logarithmic expression, which is x. And then we have the other inverse property. So if you have the log of a number, in this case the number is a, and the base of the log matches that a, so then the answer becomes whatever the exponent is there. So that is why it's good to know how to convert numbers so in other bases. So for example, the number 32, it will be pretty useful to know that that is 2 to the 5th power. Because if you had a question like, let's say this, log of 32 base 2, we could rewrite 32 so that it is with the base 2 to the 5th power, and then we could apply this amazing rule, and the answer will be 5. Okay, so we're gonna practice by rewriting some of the expressions that we have here, equations actually. These are equations because they do have that equal sign. So they're not only expressions, they all have an equal sign. And if you need to solve them, then you need to come up with a value for x, and that's what we're going to be finding here when you solve them. So we have the first one, which we already did on the previous slide. It will be 2 to the power 5. And in this case, I was showing you with a logarithmic example, but if we had the same thing that we have here, 32 to the power 2, so to what power would you have to raise 32 so that it will be base 2? So it would be 2 to the 5th. We have it here. So now that we have the same base on both sides, we could say that the answer will be whatever is in the exponent, which will be 5. Okay, next question. First, we cannot use the one-to-one property because we have a minus here and we have it equaling to 0. However, if we take this quantity, the natural log of 3, that is subtracting from the natural log of x, and we take that across, then it will be adding on the right side, or it will be positive like you can see it here. So here we can apply the one-to-one property, cross those out, and the answer will just be whatever is left for the argument. So in this case, the answer is 3. Next question. The 1/3 to the power x is equivalent to saying 1 over 3 to the power x, and so that 3 to the power x is positive because it's in the denominator, the exponent. But however, if we bring that up to the numerator, it's going to be 3 to the negative x, and so that's why that 1/3 to the power x was converted to 3 to the power negative x, just like you could see in the example here. And for 9, since we want it to also be of a base 3, then we use 3 to the power 2 because that is equivalent to 9. And so we do that so that we could cancel out the base and then the exponents become a linear quantity. In this case, we had negative x is equal to 2. So then by multiplying by 1 both sides, we get that x is equal to negative 2. So the opposite sign. For the next equation, it does say inverse here, but what we end up doing is using the inverse function of e to the x, which we know is natural log. So as you can see, natural log was applied to both. And then because the base of natural log is e, so now we can use that inverse property because the argument matches the base. So then the answer here will be x, the exponent, is equal to the natural log of 7. Now, if the question on WebAssign is asking you to enter your answer in exact form, it will be that, ln 7. However, if they want a decimal approximation, then you enter that on your calculator and then you round accordingly. So make sure you do pay attention to those little details. Okay, next one, we will use the inverse property too. And in this case, imagine that you have, and it's just coincidence that we have an E here. I'm gonna try to block it. So we could have E to the exponent ln x, and then we can do the same thing here, e to the power negative 3. So once we have done that, we apply the inverse property again because the base of ln is e. So those will cancel each other out, and then we have x by itself, and the answer will be e to the power -3, or also it could be 1 over e to the power 3. However, this will be the exact answer, but if WebAssign wants you to round, then make sure you do enter that on your calculator and round accordingly. For the next question, we use the inverse property again. We have log without a base, so you know that implies base 10. And so in this case, if we do that, we raise both of them to, we have a base of 10, and then our equation becomes the exponents of 10. So then we apply that rule, cancel, because the base matches the base of the log, and then we have x by itself, and then here we will have 10 to the power 1, -1 I should say, which is equivalent to 1 over 10 to the power 1, or just 1 over 10. For the next one, we will have a base 3, so we use the same concept, like your equation becomes the exponent of a 3, and then the 4 here becomes the exponent of a 3 as well, as long as we do the same to both sides. And remember, we do that because we want to have the base matching the base of the logarithm expression, which is the exponent right now. And so that will cancel them out. We have x by itself now, and then here we have 3 to the power 4. Right, so we cancel here. 3 to the power 4, which is 81. So that is the same as 3 times 3 times 3 times 3 is not 3 times 4. Please remember that. However, there are other ways to solve them, and I just want to show you quickly another thing you could do instead of doing that using the inverse property. So we could also rewrite things from logarithmic form to exponential form. And this is a very good skill to have. So, for example, if I have this equation here, I believe it's letter F, and so I'm going to write it. Natural log of x is equal to -3. So I know the implied base is an e, so I can rewrite this as an exponential equation, and it will be e to the power -3 equals x. Or, for example, this one here, log of x equals -1. We know the implied base here is a 10 because it's common log. So when the base is missing, it's a 10. And that, written as an exponential, it will be 10 to the power -1 is equal to x. And so, of course, from here, you will know that x is equal to 1 over 10, which is the same thing. You get the same answer. So whatever you feel more comfortable with, I'm perfectly fine with that. So let's move on to other examples. And here we have the strategies summarized. So let's just go over them quickly. First one, it says rewrite the original equation in a form that allows to use the one-to-one properties. So either the same base for exponentials or the same base for logarithms. So you rewrite the equation. The second strategy will be to rewrite an exponential equation in logarithmic form. So that's what I was showing you here, actually. I'm happy about that. This will be exactly what the second strategy is talking about right here. Strategy 2. Okay, and then of course, we have the rewrite a logarithmic equation. It says rewrite a logarithmic equation in exponential form, and then apply the inverse property of exponential equations. So, they're like, and you don't have to just pick one way or one sequence of steps. You could always, use your knowledge of the properties and see what is more convenient to you. However, I want to remind you of something. If you do not know what to do, there's nothing you can do. Like, you cannot rewrite them with the same base to use the one-to-one property, or you just can't. If you change it from exponential to logarithmic, there's nothing you can do either. So then you will take the natural, like, let's say something like this. No, not that. So yeah, let me give you a good example. So let's say that we have 7 to the power x, and then we're saying that equals to, I don't know, 100. So you know that there's no way you can rewrite 100 with a base 7. So what you will do is you will take either natural log or common log. For simplicity, I just like to take the natural log on both sides. That is always a very nice way to get out of if you get stuck on a problem. So you use natural log on both sides, and then you use the power property. So you will bring this x over here. And so that would be x now is the coefficient of the natural log of 7. The right side will just be natural log of 100. And so you notice that x is being multiplied by natural log of 7. So to solve for x, we will take that natural log of 7 across the equal sign, and from multiplying, it will go to do its inverse, so which will be dividing. And it's like you're doing using the change of base formula. Please do not confuse this with natural log of 100 over 7. Please do not do that, okay? These two are not equal, so therefore this is wrong. Don't do that. They're not the same. So when you enter something like this on a calculator, you have to physically type ln, the ln key, twice. One for numerator, then the division sign, and then one for the denominator. Okay, so we're going to do examples now. And let's see. Let's start with example A. So you see right away that the base for both equations, I'm actually going to zoom in a little bit. The base for both is e, left and right side. So then what do we say? We consider the exponents to be equal. It's a double, I forgot the name again. A double if statement, a double conditional statement. And so we say negative x squared is equal to negative 3x minus 4. Now, we have worked with quadratic equations, so we know to solve for x, we're going to have to let one side equal to 0. So I'm going to let my left side equal to 0, which means that I have to take the negative x squared across. And so that will be from subtracting, it will be positive or adding on the right side. Then I'm going to copy the rest, negative 3x minus 4. From here, I'm going to see if I can factor it. If you cannot factor, you could use the quadratic formula. And so let's see, factors of 4, I can use 1 and 4, or 2 and 2. However, I think it's going to be 1 and 4. we know that we have one of those because this sign is negative. One of the factors will have a positive number and a negative number for the other. So I'm going to choose 4 and 1. And notice how the sign of negative 3x is negative. So that means that the one with the biggest absolute value carries the negative sign. And so that will be negative 4 here, positive 1 here. Now, after this, we use the zero factor property. We take each factor one at a time. We equal it to 0, and then we solve for x one at a time. So x is equal to negative 1, and x is equal to positive 4. Now, both are good solutions because we were solving an exponential equation. So the domain of exponentials is all real numbers. So we don't really need to be so concerned about checking it. But if you are taking an exam, I will recommend that you substitute the x and see if the values that we got for x into the original equation and see if you get the same on the left and the right side. Okay, so let's move on to equation B from example 2. So here, the number 3 is multiplying to the 2 to the power x. So if I take that number across, the inverse operation of multiplication will be division. So we will have 42 divided by 3. 42 over 3 is 14, so we have now 2 to the power x, and then we have 14. So this is a very good example of like what should we do next? So one thing we can do is use the inverse properties like we went over, make this log base 2 of all of this, and then here same thing. I'm gonna make, well actually I'm gonna do it on the next row. Okay, so we have 2 to the power x, and then we have 14 here. So we can take the log base 2 of this, and here log base 2 of this. So right there, the 2's cancel out. So we have x, and we have log of 14 base 2. However, we cannot enter something like this on the calculator because it's a base 2, unless you have like one of the more advanced calculators. So, but what we can do is apply the change of base formula. So it will be the log of 14 divided by the log of 2. This will be a base 10, or we could also say ln of 14 divided by the ln of 2. Now, if we use the other method, the one that I call number 4, that it says if you do not know what to do, and we're going to solve that same equation that way. If you have 2 to the power x equals 14, and you don't know what to do, you just take the natural log on both sides. And then you use the power property, so take the x to the front as a coefficient, so x times natural log of 2 is equal to natural log of 14. So now x is going to be equal to natural log of 14 over natural log of 2. And that is the exact same thing that we got when we went the other route and used the log base 2, as you see here, and then we still had to convert it to either base 10 or base e to type it in the calculator. So I think that just taking a natural log on both sides is a pretty good way to solve any equation. Okay, so let's move on to the next slide. And here we start with a logarithmic equation, and oh great, the process of making something like this you have ln x equals 3, and then you want to make those exponents and then use the so that you can have the same base. So that process does have a name, and it is called exponentiating. So when you have an equation like this one, and then you say, I want that to be e raised to that exponent, just like we have on the next row, and then here I want this to be e raised to the power 3. So that is the process of exponentiating. It's like a fun word. So cancel that out because ln is base e. You know that. And so they cancel, and the answer is just x. And then on the right side, e to the power 3, remember that is a number. E to the power 3 will be the exact answer, but if it will be approximately something. I'm actually going to pause the video and find what it is. So the approximation for e to the power 3 will be 20.08. I'm going to round to 4 digits after the decimal point. So 20.0855. So let's do more examples. Now we're going to move on to logarithmic equations. And I just want to see how many. Okay. Let's solve this too. And then I want to check on your textbook what are the examples that they did not include in the PowerPoint so that we can have more. Okay, so we have natural log of x equals 2. What we could do is exponentiate each side. So it will be e and e. We will have here ln x equals 2. I mean e to the power 2. Then, of course, this 2 will cancel out, so x will equal e to the power 2. And if we were asked to enter an approximation of that, it will be e, well, hold on, 7.389 if I round it to 3 digits. Make sure that you read the instructions on how you're supposed to enter your answer on WebAssign, because if they do not ask for rounding, then they are implying that they want the exact answer. And if they ask for rounding, then make sure you enter a decimal answer approximation and round accordingly. Next problem. We're going to go ahead and use the one-to-one property because we have log base 3 on both sides. So that is pretty easy. We could cancel those out. And the idea, let me tell you why we can do that actually. If we exponentiate that to 3 and 3, then we have the same base here as we have it here, and same thing here, we have that. So that's another reason why. So we have 5x, actually I don't need the parentheses anymore. 5x minus 1 is equal to x plus 7, and so this will be 5x minus x is equal to 7 plus 1. So one step, and we're almost there. So we have plus 1 because it used to be negative here. So on the right side, it will be plus or positive, goes from subtraction to addition. And with the 7, we had positive 7. So now is, no, wait, positive x. And then we have negative x here. So that's what I did. I took that one to the left, and then I took the one to the right. Now we can combine like terms. So 5x minus x is 4x, and then 7 plus 1 is 8. And to solve for x, we have 8. We're going to divide by 4 because the 4 is multiplying x, and that will give me x is equal to 2. And so we're great there. For the next example, we will be using the one-to-one property. However, we cannot use it yet because we have 1 log base 6 here, but here we have 2. So what we're going to have to do first is to use the quotient property of logarithms from section 3.3 so that we can condense those 2 logarithms into 1. And so because we have a negative sign in front of log of 5 base 6, then that indicates that we will use the not the product property, but the quotient property, in which we will have 3x plus 14 in the numerator the argument of the logarithmic quantity that has a positive sign goes on top, and the one with the negative sign in front of it, the argument which is 5, it goes on the bottom, just like that. Then on the right side, we only have log base 6 of 2x, so that will be fine. Now we can go ahead and apply the one-to-one property because you have log 6 both on both sides only once. That you cannot just like use the one-to-one unless you have condensed an expression like that. And so after you do that, you will have 3x plus 14 is equal to 5, and then we have 2x on the right side. So the 5 is very clear that it's dividing, so we're going to move it across and it will be multiplying. So we will have 2x times 5 and so we will have 3x plus 14 is equal to 10x. Then from here, we want to keep our x's on the same side. And just because 10x has a bigger absolute value than 3x, I'm just going to keep 10x on the right side. And then I will take this positive 3x across the equal sign. So it will go from adding to subtracting, or from positive to negative. And here we still have our 14 on the left side of the equation. So we combine like terms. 10x minus 3x will be 7x. And then now 14 divided by 7 is equal to x, so x is equal to 2. Okay, next we will have an example. In fact, I'm going to pause and see if I can get other examples that will be worth to include here before we get to our, I believe this is our last problem. Yeah, it's our last problem. So I'm going to pause it. Okay, so I'm going to write the extra examples over here. So let's see. For example 3 from your textbook. Let's see. This is just to give you more examples. So we have e to the power x plus 5 is equal to 60. So what should we do here? We have a plus 5 here. So if we take that across, it will be 60 divided by 5. So e to the power x is equal to 12. And from here, we all know that we can take the natural log of e to the x, take the natural log of 12. And so that will cancel out. We get x here, and then here we have natural log of 12. And that will be the exact answer. For an approximation, you will just have to enter that on your calculator. Okay, so I'm going to go ahead and copy example 4. And that is 2 times 3 to the power 2t minus 5 minus 4 is equal to 11. So here we're going to use some steps. First, we need to take this minus 4 across. So it's subtracting to the expression that has the variable, the unknown variable. So I need to take it to the right side. So then we have 2 times 3 to the power 2t minus 5 is equal to 11 plus 4. Then, of course, we add those numbers, 15. And now you could see how this 2 here, it is multiplying to 3 to the power 2t minus 5. So it's multiplying to everything inside the parentheses. And so we're going to take that 2 and take it across. So from multiplication, it's going to go to addition. Actually, I don't need this parentheses anymore. That will be 2t minus 5. It's equal to 15 divided by 2. Now here we actually have a pretty good example of what I was saying about taking the natural log. And that's what we're going to do. Now, I do not want you to round this. Just leave it like that as a fraction. In fact, this one is easy because it's just 7.5. So let's just do that. So what we're going to do is, like I said, take the natural log on both sides of the equation. And then what we're going to do is take the exponent from here and move it so that it is the coefficient, 2t minus 5. Then we have here natural log of 3 is equal to the natural log of 7.5. Okay, so now because natural log 3 is multiplying to everything inside the parentheses, the 2t minus 5, we will leave the 2t minus 5 here on the left, and we're going to take this quantity across, so it's going to be dividing on the right side. And so that will be natural log of 3. Okay, now here, please do not even think about canceling natural log. You cannot do that. Just don't do it. But what we're gonna do, and I don't want to like round too soon, enter this on the calculator and get some, have to like approximate the decimal or truncate the decimal, and then, you know, I will be missing something. So I'm just gonna leave it like that. Instead, I'm gonna take, I'm gonna leave it in parentheses actually. Like that, and we would take this plus 5 across the equal sign, so now it will be adding plus 5. I mean, the negative 5 across, it will be a plus 5. And then lastly, the 2 is multiplying to t. And so if we take that across the equation, I'm going to please first write what I already have. And then we're going to divide by 2. Now, all of that will be the exact answer. However, if you enter this on the calculator, you have to, of course, include this parentheses here and here. You also need to make sure you have ln twice, but also you need an extra parentheses so that you can enclose the numerator. And then at the end, you just enter divided by 2. Or you could first find the ratio here, then add 5, and then at the end divide by 2, as long as you follow that order. So this t is going to be practice on your calculator, see if you get the same, approximately 3.417. Okay, and let's see. Let's do example 7. It's also from your textbook. I just didn't think this PowerPoint came with enough examples. So we have the equation 5 plus 2 ln of x is equal to 4. So we start by taking the 5 across, so it will be 4 minus 5. So we subtract 4 minus 5 is going to be equal to negative 1. Then we have 2 ln x. Remember, this goes together. So the 2 is multiplying to the natural log of x. So we're going to take that across. It will be dividing. So we have negative 1/2. And now from here, we could exponentiate both the natural log and the 1/2. Or we could also convert to an exponential expression, and so that will be e to the power negative 1/2 is equal to x. And so that will be the exact answer, but if you have to enter it on the calculator, make sure you do, once you press your key for e, whatever it is, your calculator screen might open a parentheses for you, but sometimes it doesn't. So if it doesn't, make sure you enter parentheses and then negative 1/2. And remember, you have to use the negative sign that is below number 3 on your calculator. The little negative that looks like it has parentheses around it. Okay, so the answer to this will be approximately 0.607. So for example 9, the equation will be 8 We already did 9. 8. 2 log base 5 of 3x is equal to 4. So what can we do here? First thing, take that 2 across is multiplying the logarithmic expression. So if we take that across, it's going to be dividing. So we will have log of 3x base 5 is equal to 4 divided by 2. You'll know that's equal to 2. Now we have log base 5 of 3x here. So one thing I would like to do here is exponentiate. So that means we put a 5 here, we put a 5 here, and we make the left and right side of our equation the exponents. And here 2, we need the equal sign. So we do that because we want to cancel the base with the base of the logarithmic expression. The logarithmic abbreviation goes away too. So now we have 3x is equal to 5 squared. We all know what 5 squared is. 5 squared is 5 times 5, so that would be 25 is equal to 3x. The 3 is multiplying, so if we take that across, it will be dividing. And so that will be the exact answer for that. If WebAssign requires you to give an approximation, then just enter it on your calculator and round accordingly. Okay, so now we did enough examples, I think. So we're going to go back to our where we left off. We did example 9, that was already in the PowerPoint. And so now we can move on to example 10. So example 10, it says you invest $500 at an annual interest rate of 6.75%, and it is compounded continuously. How long will it take for your money to double? So the question is how long? So the question is, what is time equal to? Now, the part that says continuously tells me that we must use this formula. Remember in section 3.1, I believe that's where we introduce continuous compounding and other types of compound interest, such as annually, semi-annually, monthly, daily, weekly. And for that, we had another formula that it looked like this. 1 plus r over n, and then nt. But I remember telling you, if you see the word continuously, it must be that formula. So I'm just going to erase this one for now because we don't need it. I don't want to confuse you. So we have that the principal, the money that was invested was $500. And we have that the rate, it is converted to a decimal, so we have to divide by 100. In other words, move the decimal point 2 units to the left, so it will be 0.0675, like that. And then t is what we're looking for. And then we need something else, because so far if I substitute, remember e is just a number, it's not an unknown variable. So we have r, which is 0.0675, and then multiply by t. So t is what we're solving for, the time, how long would it take? And the question also says for it to double. So if we know the original investment is 500, double of 500 is going to be 1,000. Sometimes you may encounter a problem where you don't know what the initial value is, but if let's say we didn't know, we could still use P for principal, and then here we will use 2 times P, and it will still work out, and you will be able to find the time. Or if it's a triple, you would put a 3 here. But in this case, we know it's 500, so that's fine. So we start there, and then first thing we got to do is take this 500 across. The 500 is multiplying e, so then we take it across. It's going to be dividing. And so you know that 1,000 over 500 is equal to 2. And so we could now solve for t. So, oh, and in fact, we had space to do all this here. So here's what's telling you that the final amount to double will be 1,000. And then we have 500 times e to the is it negative? No, it's positive because it's interest. Interest grows. So I'll just make it a decimal point, 0.0675t. So it says here first, divide each side by 500. So we know that equals to 2. Then after that, we're going to take the natural log. Actually, the 500 is not here anymore. So we take the natural log. So natural log of that of 2 equals natural log of e to the power 0.0675t. So here you know ln is base e, so that will cancel out. Your exponent becomes a linear quantity. And here we still have natural log of 2. We don't need to put it in the calculator and get an approximation because then we might be rounding too soon. So what we do now is we're solving for t. So you could see that the 0.0675 is multiplying t. Take it across. So it will be doing the inverse operation. So it will be dividing ln 2. So you will have to enter first on your calculator natural log of 2, then your division key, and then you can enter the decimal 0.0675, and you will get an approximation of 10.27. So you could see here, that's the amount of time that it will take for the 500 that were initially invested to turn into 1,000, 10.27 years. And that is at a continuous rate, compounding with a rate of 6.75. So 10 years. Okay, so this is the last problem. End of the video.